Our last section in this module is counting binary trees. As I have mentioned at the end of the video for lecture 7.4, we are not going to go to the detail of this counting process, as this involves a much more intricate mathematical concept called the moment generating function, or in general generating function, and we're going to skip those ideas, even though in the lecture that I have posted it for you, that's on page 2. I'm just going to go over the basic ideas of counting on binary trees. So we close this section with a formula for the number of different binary trees with n vertices. The formula is derived using generating functions, although the complete details are beyond the scope of this text. We will supply an overview of the derivation in the order and illustrate how generating functions are used in advanced commentaries. So let Bn be the number of different binary trees of size n with n vertices, n greater or equal to 0. By our definition of binary tree, the empty binary tree will have no vertex, so B0 will be 1. Now consider any positive integer n plus 1, n greater or equal to 0. The binary tree of size n plus 1 has two subtrees, the sizes of which add up to n. The possibilities can be broken down into n plus 1 cases. So case 0, the left subtree has a size 0 and the right subtree has a size n. Case 1, the left subtree has a size 1 and the right subtree has a size n minus 1. So the sum must be equal to n. Similarly, case k, the left subtree has a size k and the right subtree has a size n minus k. And case n is the left subtree has a size n and the right subtree has a size 0. In the general case k, we can count the number of possibilities by multiplying the number of ways that the left subtree can be filled, which is bk, because the size of the subtree is k, by the number of ways in the right subtree can be filled, which is bn minus k. Again, the sum is n minus k. Since the sum of these products equals bn plus 1, we obtain and have a recurrence relation n greater or equal to 0 given by bn plus 1 in state 0 or case 0, b0 times bn. In case 1, b1 times bn minus 1. In case k, bk times bn minus k. And in case n, bn times b0, which is written as a sigma sum of k equal to 0 to n, bk times bn minus k. At this point, we're going to borrow help from the generating function. And I'm going to skip this calculation for the lecture, for this class. But if you are interested, generating function is a module that we skipped for our class, Introduction to Discrete Mathematics, in this summer session. But the book that I have assigned for this class, if you go, you will find the section for generating function. And this is fascinating idea. And especially if you are a computer science major, there will be a time in your life when you will be encountering generating function for sure. It's just not part of our curriculum. So I have given you the work, and I'm going to skip that work and just tell you the final result that we get. So it turns out, after a lot of calculation, that the closed expression for the number of binary trees with n vertices, bn, is given by 1 over n plus 1 to n choose n. This sequence of numbers is often called the Catalan numbers. For more information about Catalan numbers, see the entry A000108 in the online encyclopedia of integer sequences. So I'm going to stop lecturing there and show you related problems, not exactly depending on this formula, but problems that are related with discrete mathematics and binary tree structures. So let's talk about them. Our first exercise is asking us to prove that a maximum number of vertices at level k of a binary tree is 2 to the power k. And this result is pretty simple. So let's try to understand that. I'm going to do it by induction. So we'll start at level 0. Remember, this is the root, and there is exactly one vertex. That is 2 to the power 0. That makes sense. So basis of the induction makes sense. Your induction starts at 0 and it is good. Assume that at level p greater or equal to 0, number of vertices, so this is called induction hypothesis, the number of vertices be 2 to the power p. And I'm going to prove it for 2 to the power p plus 1. So now, for each of these 2 to the power p vertices in level p, there is at most 2 edges connecting 2 vertices at level p plus 1. That's pretty simple to understand. I'm going to give you a small example here. So this is the root. The first level, I say, have 2 vertex. And then I have, for each of them, 2 more vertex. So that's exactly what I'm seeing. Say, this is my level P. Then I have at most 2 edges, because it is not necessary that I won't have both left and right graph. So at most 2 edges at level P for each vertex connecting to 2 more vertices at level P plus 1. So the one other thing that I want to change in this proof, when I say that assume that at level P greater than 0 number of vertices be 2 to the power P, I should actually say, because it is talking about the maximum number of vertices, be less than or equal to 2 to the power P. I just want P. So I want to show that this is the greatest possibility, be less or equal to 2 to the power P. And that should be fine, because I want to show that for K, the number of vertices cannot be exceeding 2 to the power K. So that's where we're getting to. So now think about this. At level P, the most number of vertices is 2 to the power P. Now for each of these 2 to the power P vertices, I have 2 choices of vertices. So total vertices at level P plus 1 is how many? It's going to be 2 to the power P times 2 or less, depending on how many vertices I have at the P level. So that is 2 to the power P plus 1, which ends the induction. I have assumed that the result is true for the Pth level and shown that the result is also true for the P plus 1th level. Hence the result is true for every level. So hence I get to say at level K, that's a general natural number, there are at most or the maximum number of vertices 2 to the power K many vertex. And this is also going to help us understand how many total vertices are there at level K from level 0. So what do I mean by that? Let's look at the second half of this question. Now it says, prove that a tree with that many vertices at level K must have 2 to the power K plus 1 minus 1 vertices in a total. So think about this binary tree and say it's a full binary tree with all possible edges everywhere. So this is my situation. So at level 0, this is a 0th level, you have 1 vertex. And then you have at level 1, you have 2 vertices. At level 2, you have 4 vertices. But how many total vertices you have? 4 plus 2 plus 1. So let me do one more stage. And then I will tell you the formula. So at level 3, I have 1, 2, 3, 4, 5, 6, 7, and 8. So that's 2 to the power 3. Makes sense with our previous work. So the total number of vertices that I have from 0 level to level 3 is 1 plus 2 plus, and 2 can be written as 2 to the power 1. Then the next step, level 2 is 4, which is 2 squared, and this is 2 cubed. These type of series, sum of numbers, are called geometric progression. And the nicest thing about a geometric progression is that there is a formula to find their sum. And what is the formula to find their sum? It is the first term of the sequence multiplied by multiplied by the common ratio. Common ratio is the number that you are multiplying every single time to get the next term. So times the common ratio to the power the number of terms in the series minus 1 over the common ratio minus 1. So let's use that example, that 1 plus 2 to the power 1 plus 2 squared plus 2 cubed, to find the sum of the total number of vertices. See, the first term is 1. Every time I'm multiplying 2 to get the next term, so that's the common ratio. There are a total of 4 terms, so this is 2 to the power 4, minus 1 all over 2 minus 1. So how much I get? I get 2 to the power 4 minus 1, and that is equal to 16 minus 1, and that's 15. So let's count whether I have 15 vertices or not. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Answers your question. But I will prove that in general. So I'm not going to do much. I'm going to use this formula one more time. So it says if you have 2 to the power k many vertices at the kth level, then the total number of vertices from level 0 to the kth level is 2 to the power k plus 1 minus 1. So what I'm adding? 1 plus 2 to the power 1 plus 2 squared plus 2 cubed. And I'm going to do it till I reach 2 to the power k. That's the total number of vertices. Initial term, the first term is still 1 times, common ratio is still 2. How many terms I have? Well, you have, starting at 2 to the power 1 to 2 to the power k, you have k many terms. Then you have 1, so then you have k plus 1 many term, minus 1 over the common ratio is still 2, minus 1. And that is 2 to the power k plus 1 minus 1, exactly what we wanted to see. So the total number of vertices in a tree that has 2 to the power k many vertices at the kth level is 2 to the power k plus 1 minus 1. And this is a very nice counting formula that we have found for a full binary tree.